Welcome to the ICMS virtually. I want to start by just telling you a little bit about ICMS before moving on to introduce our speaker today. The ICMS is the International Centre for Mathematical Sciences based in Edinburgh. It's one of two research institutes funded by the UK government across general mathematics, so we're not with a specific mathematical focus in mind. The other being the Newton Institute in Cambridge. And at ICMS, we run research workshops and intensive research visits for people. So we're in the process of actually creating mathematics and getting people together to create mathematics. Our research workshops are typically 1 week long, whereas, for example, the Newton Institute will run things that last 2 or 3 months. So it's a very different rhythm that we have at ICMS. We also promote a lot of knowledge transfer, knowledge exchange type activity, and are very committed to our public understanding events. And of course, public understanding means public lectures. And it's wonderful to be able to showcase mathematics in this way and have wonderful online events now, and not just restricted to Edinburgh. So moving on to today, our speaker today is Professor Tanniemola Liverpool, who is Professor of Theoretical Physics in the School of Mathematics at Bristol. Tannie works on the mathematical description of complex fluids and soft biological matter. He did his undergraduate and postgraduate degrees at Cambridge, and his PhD supervisor was someone I know quite well, knew quite well, Sir Sam Edwards. After a postdoc in Germany, he obtained one of those prestigious Royal Society research fellowships and came back to work in Leeds, and he then moved on to Bristol. As well as an extremely active research career, Tannie has found time to be involved in many initiatives encouraging diversity within the physics and mathematical communities. Tannie's research brings a deep mathematical understanding to an incredible variety of natural phenomena at many different scales. So there's sort of really interesting breadth of interest and scale of interest. So you're moving from small scale to large scale, both physically and in time. His title today is The Mathematics of Active Matter, and it's probably best if I let him take it from here. Thank you, Tannie.
Okay. Okay, so thanks, Paul, and to the organizers of this seminar series for the kind introduction and invitation. So let me begin by trying to explain the words in the title, in particular the last two, active matter. So, and I'll try to do that by using some examples. So, consider the videos on this slide. So on the top right-hand corner, you've got a murmuration of starlings, a bird flock. On the top left corner, we've got a colony of E. coli bacteria. And at the bottom, we've got a microscopic video of the development of a fruit fly embryo using a newfangled type of microscope called a light sheet microscope. And we're seeing what is called the segmentation of the embryo there. So you can sort of see. And you can sort of see the scale there is 50 microns at the bottom there of that image of that video here. So this object is therefore of the order of maybe 100 or 200 microns, a few hundreds of microns. Whilst the bacteria is typically of the order of maybe a micron, and of course the birds are much larger. So these are very different systems. So you would be well within your rights to think, is there any sense in which they can be described by the same framework? And I guess what I want to try to convince you in this talk is that in some sense, indeed, they can. So first thing you're going to say is, why have I called these disparate systems active matter? And I guess the first step, of course, is matter, okay? So I just want to remind us what we usually mean by matter, as we learned it in secondary school science. And we usually say matter is anything that has mass and occupies space. That basically means pretty much any physical object. The other thing I want to highlight is equilibrium. I need to sort of say what I mean by equilibrium. So, and you could sort of say that matter at equilibrium is any physical object, that's matter, which left to its own devices does not go anywhere or do anything. It just stays there. And of course, we often talk about the state or phase of matter. And of course, we hear about the solid, the liquid, and the gas phase. And of course, taking water as our material, then we know that we have ice, water, or steam, and those are water in three of those phases. So, and of course, as I said just now, these three phases are made up of the same molecules. So hence the difference between them must be an emergent property. So understanding emergent properties is something that's been something that's obsessed me for many years. Okay, so how do you get emergent phenomena? Basically, there are usually two ingredients. One, many molecules or atoms, depending on the material you're talking about. And the other thing is interactions between those molecules or atoms. And it's somehow these interactions and the fact that you have many molecules that causes these phases to emerge. And that's the kind of picture that I want you to bear in mind as we go forward in this hour or so. Okay, and now going back to the systems that I showed, the videos that I showed before, let's compare them to matter at equilibrium, our glass of ice or water. They both have many interacting particles. In one case, the particles are molecules. In the other case, they are birds or fish or something. But the water stays put, whilst the active matter does not stay put. And so essentially, that is the thing that we need to bear in mind, is interested in many interacting things that do not stay put. And so, so then you can also ask the question, why would you study, what's the interest in these? Of course, there's obviously the fundamental interest in them, which is, it's always interesting to study things that are interesting and hard to understand. But in fact, there are lots of places where you find many interacting elements which don't stay put. Crowd control, whether it's human or otherwise, is something that's clearly usually highly desirable. So at the bottom of this image, I've got a picture. The bottom image here is a picture of the Shibuya crossing in Tokyo, which is supposedly the world's busiest pedestrian crossing with up to 3,000 people crossing at any time. And as in general, there are many scenarios where you can imagine that you want to be able to optimize such places where you have large numbers of individuals who are moving and interacting. And then something which is a little bit more science fiction-y is the idea of making smart materials, making materials which will respond to their environment. And this is something which is very much for the future, but people are already starting to show that you can have programmable self-assembly using self-propelled robots, which is the video that I have on the top left-hand corner. And so things like that could probably be the starting point of understanding sort of these smart materials. Okay, so before we get started, I want to develop some mathematical notions which we'll need to help us along the way. So first thing, I want to talk about our functions. So let's consider my weight since the lockdown. So at t equals to 0, i.e. lockdown, we're going to measure time from the lockdown. I started with some initial weight, stayed home, didn't do much, and my weight went up. Of course, I noticed it. Then I started doing some exercise, and my weight went down almost to its initial value, but then I started losing a bit of motivation and was doing less exercise, and my weight started creeping up again. Till today, where it is somewhere in between my initial weight and my peak weight, let's say. So my weight, as it varies through time, is an example of a function, and this function has an input t, the time, and an output, which is my weight, which you call it f of t. And I can show my weight as a curve whose height above the time axis is measuring my weight. Higher height, higher weight. So you see this curve, this blue curve. That's the function. So that's basically, that's what a function is. It's some curve. Okay, so let's look at a function in a little bit more detail. So the rate of change of a function with a variable, now in this case, let's say time, measures how fast the function changes as the variable is changed. And that is called the derivative. Again, many people will be familiar with this. And when this function is increasing, the derivative is positive, and when the function is decreasing, the derivative is negative. And of course, we are used to the fact that the derivative at a point is equal to the slope of the line touching and parallel to the curve at that point. Okay. Another operation that one can make on a function is to integrate it. And the integral of a function between two values, in this case, a and b, is the area under the curve defining the function between a and b. Again, okay, bear with me whilst I go through these notions. They're helpful to kind of get a sense of what we're going to do, of the mathematics of what we want to do. And we can generalize our definition of a function to two variables. For example, we could measure my weight as a function of time and height from the ground. So we know that at very large heights, let's say in space, I will be weightless. And so let's just taking one of these axes as being my weight, as being time, and the other one as being height. And then my weight would be given by the height of this surface above this plane. So the function is now a surface, and the integral is now the volume under the surface. And clearly, we can generalize this to functions of n variables, x1 to xn. And you can sort of already see that I'm going to be thinking of n being very large, like the number of interacting entities in my matter, whether be it passive or equilibrium. So now let's get back to atoms and molecules of matter, in particular matter that stays put, that doesn't move. Since matter is made of atoms and molecules, and I'm gonna call them particles, then the state of matter must be encoded in what the particles are doing, because that's what it is. That is where they are, their positions, and how fast they are moving, their velocities. And this video is a bit of a schematic of a bit of matter looking rather gas-like, I would say. So let's denote the particles by a label, which I'm going to call I. So the and I is going from 1 to n. And I can denote the position of each particle by a vector Ri and its velocity by another vector Vi. And the number of particles, n, for which you would have in, let's say, a glass of water, would be of the order of 10 to the power 23, which is a 1 with 23 zeros after it. So a rather huge number. So you have a large number of these molecules. And these molecules must obey the laws of physics. And let's take for them here Newton's laws. And Newton's laws, if remind us, particles move with a constant velocity unless compelled to do so by an external force. That's Newton's law. And the rate, that's the first bit. So particles move in straight lines unless there's forces. And the rate of change of the velocity is proportional to the external force. The bigger the force, the bigger the change in velocity. So they would move at a constant speed in a straight line unless there's forces. So the velocities, of course, we know, again, high school science is the rate of change of the position. So the derivative of the position with time. And the second bit of Newton's law says that the rate of change of velocities is proportional to the force. So we don't know what the forces are. So that's the last bit. We know the velocities. Velocities are just rate of change of position. What's the forces? Okay. So to focus our minds a little bit, let's look at the trajectory of a single particle from a time t equals to 0 to time t equals to t, capital T. So it only changes directions due to forces on it. And these forces are going to come from the other particles. And as you can sort of see, since the velocity is the rate of change of the position, the velocity is just given by the tangent to the curves. And the forces, you can see there's forces wherever the curve changes direction. So the question, so the next step is, what are the forces? Okay, and how do they affect the emergent behavior? And effectively, they emerge because there are interactions between the particles. And this interaction usually has some generic features. When two particles come really close to each other, they apply repulsive forces to each other. And when they are very far apart, they don't affect each other. I mean, typically people talk about short-range interactions. And it is what happens in between that determines the emergent behavior. And for many particles, there's going to be a range of distances when the particles will feel an attractive force. So they'll have short-range repulsive forces always, long-range, they don't affect each other. In the middle, there could be some attractive interactions. And this essentially is what leads to these different phases. And this can be encoded in a function, which we call the interaction potential, which depends on the separation between a pair of particles. So this interaction potential, call it U, R12, depends on the distance R12 between particle 1 and particle 2. And there are lots of different models which will correspond to different, if you want, molecules. And a very popular model system which describes many molecules is called the Leonard-Jones potential. John Leonard-Jones, by the way, was an applied mathematician who was professor of physical physics at Bristol. And so this potential has the usual form. It's repulsive at short distances. And then, you can see that by looking at describing the force in terms of the potential. So the force is given by the gradient of the potential minus the gradient of the potential. So essentially the slope of this curve is going to tell us what direction the force is. So if we look at the bit when r is close to 0, we see the slope is negative. So that tells us the force is going to be positive. So the force is going to be pushing you away. So that's going to be repulsive. If you look at this regime here, when we're far away, the slope is positive. So the force is negative. So there'll be an attractive force. So you'll have an attractive well. And so this attractive well then is going to play a big role in what happens. Okay, so now we know what the forces are. Once we have the potential, we can write down the forces. So so now we have a well-posed problem. We have two equations of motion, and there are and we know how to solve such equations in principle, but we have too many equations because we have one with 23 zero equations. And so no matter how clever we are, this is computationally intractable beyond billions and billions of times more powerful. A computer billions of times more powerful, the best computer today could not deal with this kind of problem. So solving the equations is basically intractable. And so we need to resort to other methods. And actually, this is where we can resort to probabilistic or statistical approaches, and leads to the field of statistical mechanics. Okay, and so let's us be concrete, and let's try to understand the existence of phases. So let's consider a fixed amount of material. So let's say a glass of water on a table. Okay, and of course, we put the glass on the table and it stays put, it doesn't move. Okay, so the key insight is that equilibrium must mean that the system is stationary, and the particles, individual particles which make up the system, are possibly moving. So describing such systems we should use this information that about the systems being stationary. Okay, so now, so we know the equations of motion, but they are too complicated to solve, so we need to resort to other techniques, and what we're going to have to use is probability. So we need, in order to do this, we need to develop some simple notions about probabilities. So imagine we have a normal dice and consider making a large number of throws of the dice, okay? And so you can count the number of times you get a 1, 2, 3, 4, 5, 6, those are the only options. And we call them N1, N2, N3, N4, N5, N6. Clearly adding all the numbers together must give you N, because that's the total number. And so we can define the probability of throwing a 1 as N1 divided by N, and the probability of throwing a 2 as N2 divided by N, and for the probability of throwing an I as Ni divided by N, where I goes from 1 to 6. So everything fine. Clearly, adding the probabilities gives N divided by N, so that just gives us 1. And so we get the general rule that the sum of probabilities is 1. And of course, for an unbiased dice, that means that that side has a probability of 1 over 6. Now, we can get the average score by noting that actually the middle of this is going to be between 3 and 4. So the average score is going to be 3.5. That's 3.5, that's not. But actually, using the probabilities and averaging over them, we can actually calculate our average scores. So if we sum over all the i's and weight each I by the probability, we get 3.5. And that's why probability is interesting, because once we've got the probability, then we can calculate the average quantities of any property. So using probabilities and averaging over them will tell us how likely any scenario is, and in each particular, which is the most likely. So now we want to use probability to study the states of matter. And then eventually we want to use probability to study states of active matter. And so equilibrium statistical mechanics, which was using this statistical approach to study these systems, says that rather than individually following the dynamics of an essentially uncountable number of particles, we're going to focus on their average behavior. And so for this, we need the probability of finding the particles with a particular position, with particular positions and velocities. So for example, the probability of finding particle 1 at position R1 with velocity V1, particle 2 at position R2 with velocity V2, and so on. So, and to be concrete, we're going to generally be considering n particles in some volume V. And we can define a density, which is the number of n divided by v. And of course, here we can also use the probability of the fact that the sum of the probabilities add up to 1 means the integral of this probability over all the possible positions of momentum must give us 1. So, so remember, equilibrium, everything stays put, nothing moves. So Boltzmann, Gibbs, Maxwell, and others told us, have given us how to calculate this probability of persistence at equilibrium. And the key insight is that this probability depends only on the total energy of the particles. It doesn't depend on precisely what the particles are doing. So once we have that, we can calculate averages and hence the properties of this material. And so there's a fair amount of technical difficulty in doing this because essentially it boils down to doing multi-dimensional integrals, and these integrals in general are hard. And there are and people have spent the intervening 100 years calculating away at doing these integrals, and we've developed very good approximation techniques for doing them. You could say essentially. But going back to our system of ice, water, steam, we can understand the behavior this emergent behavior quite simply. First thing is the temperature of the material is essentially the velocity squared. Essentially, the higher the speed, the higher the temperature. And if you increase the density, you can increase density by increasing the pressure. And basically what you find is that at high temperature and low pressure or low density, you have a gas, which is in the sort of top left hand corner of this picture. At intermediate temperatures and pressures or densities, you have a liquid. And at low temperatures and high pressures, you have a solid. And so of the liquid, you can sort of see the free surface of the liquid there. And so it's essentially the particles are, it's essentially incompressible, but the particle can move around each other. The solid, the particles are in a nice crystal lattice. And essentially we can identify the boundaries between the phase and understand the transitions from one phase to another, which is sometimes sudden and sometimes smooth. And essentially, the main thing you should know is that changing the potential moves the phase boundaries. So, so the details of how, and basically by doing this calculation with different potentials, you can calculate different phase diagrams. And this has been done very successfully for the last century. And the details of how this range of attractive forces leads to phases, of course, subtle and requires some lots of what I would call nice mathematics. But it's a very successful framework that works and is completely clear on how it works and why it does. And essentially, we see it becomes it becomes quite precise that the emergence is a collective phenomena of all these molecules. So let's just kind of review what we've done here. So we essentially have this dynamics, which we can write down, but which we basically can't solve, has way too much information. We need to use averages and probability, noting the fact that the energy is constant, And then we can essentially calculate what the typical particle is doing. And so essentially what we've done is we've focused on the useful information. We've extracted this information from the system, and this works very well. So now the question is, what happens if we try to do this for the active systems that we talked about at the beginning? So, so we have a similar situation, a large number of particles, but energy is not constant. And we also know, we can see that they're not staying put. And of course, the reason why they're not staying put is because most of the things, there was a flow of energy into the system. You had a bird or a fish which was using up its energy to swim or fly. And the question is how to build a framework to describe them. And of course, really what you want to ask is, how is the collective behavior, how is the emergent behavior linked to the way the energy enters and the interactions? And of course, a key step of that is to look at simplified man-made systems which have some of these features. And that's what I want to tell you guys about next. So I'm going to talk about an experimental setup which was studied by my friend Denis Barthelot from Lyon in France. So, so what he has are small plexiglass spheres which are in a chamber surrounded by a conducting liquid between two electrodes, and which is connected to an electricity supply. They sediment at the bottom of this chamber, and then when at a big enough electric field, they start rolling in a random direction along the bottom. And again, the point is that this is not stationary. So you can sort of see that this flock is moving in a deterministic way along this channel. And of course, I like the channel because it's a very nice system, but of course he did it in many different shapes and shows different shaped chambers and got this type of behavior. So what do we have? So you have this flock which swarms. So I should say that each dot is a particle of one of these spheres. So this is an example of a synthetic flock, if you want, which is showing this swarming behavior. So there is now a similar setup up and running in Bristol, which has been run by colleagues in physics and chemistry. And so this is Abraham, Jerome, and Paddy, and they're studying in detail the phase behavior of these systems. So again, trying to understand the emergent behavior of this system. And I'm going to show you a video of some of their experiments. And what only thing you should look at this video is that the spheres are color coded, and when the local environment of the sphere is more crystalline, it's blue, and when it's more fluid-like, it's red. So you can sort of see that this cluster is building up, which is becoming where the center is somewhat blue. So let's look at a few more videos. So in this video, the electric field is increasing with time. And you see at low fields, there seems to be a stationary crystal, like a solid, which then becomes motile as the field is increasing before dissolving into sort of like a gas-like flock. And the right-hand picture is the same as we had before. So let's look more closely at what happens as you increase the E fields. So this is at fields where we saw this crystal breaking up. So what you can see here are amoeba-like clusters, which are splitting and coalescing. And thing you should bear in mind is that you could never see this kind of behavior in a normal material. It's not a liquid. It's not a solid or a gas. So really what we want to do is to develop some framework to describe such phases. So let's try to describe what's happening to these particles mathematically. So we can make a sort of a minimal model equation for the dynamics of the rollers. And each particle is defined by a position of its center, but also its rolling direction. So which I'm going to specify by an angle theta. So there are going to be forces and torques due to interactions, but the thing that's going to make this, that makes the system active is this rolling speed. And we're going to specify the speed of the rolling by this parameter Fp. And I've said red because it's red because red makes it active. So if you didn't have this would basically look just like some variant of an effective particle, and it could be described by equilibrium statistical mechanics. So the fact that it's got this Fp being non-zero is what makes it active. And of course, there are interactions. I don't worry too much about that. Maybe the only thing I will say about the interactions is that the interactions have a hardcore repulsion, and they'll have some attraction in the normal way that we've discussed before. But the only thing I want you to focus is that we're going to have two control parameters. I'm going to make some dimensionless numbers, one of which is going to be measuring this activity or the rolling speed, or how fast, which is essentially electric field. And the other thing is going to be how crowded it is. So it's like a density. This is in 2 dimensions, it's going to be an area density. And we want to understand what the phase behavior of this system is as we vary these parameters, the same way that we asked about when we vary the gas with temperature and pressure or density. So now we are in a situation, similar situation to Boltzmann and Co. a century ago. We've got many equations which are difficult to solve, and we also have too much information. There's just we want to know the phases. We don't really want to know what every single particle is doing. So we basically need a new prescription for how to get this probability. And I should just specify here that our variables are going to be the position of each particle and its rolling direction, given by the angle theta it makes with some axis. So unfortunately for us, well, you could say it's unfortunate because you could say we can't just use what was there before, but fortunately, because it's also interesting, there's no energy conserved, because then it's not constant. So we clearly the probability is not going to be proportional. It's not going to be a function of the energy. But actually, what we can do is to look for conserved quantities of the dynamics, things which don't change in the dynamics, and maybe we can and try to build this distribution out of these quantities. And in fact, this is what we have done. So we can find a function. I'm not going to bore you with the function. A function of the variables, but it's a function of all the variables. So it's not going to depend. It's going to depend on what part we're doing. But it's not going to be very sensitive to what one particular particle is doing. It's going to be sensitive to what all the particles are doing together. And it's going to be, and we can build this probability out of these quantities and find this probability. But what one finds when one does this is that, in fact, the particles typically will be moving. So in equilibrium, we know that on average, the particles are not moving, even though individually they are moving. Here, what you find is that on average, the particles will be moving, which of course is what we can see from the experiments and from the motivation. We want to describe such systems. So now it turns out that you can find these functions only under certain conditions, and that by that I mean for certain types of dynamics and certain range of parameters. And identifying these conditions is actually what is mathematically rather subtle, and is actually what I spend a large part of my time doing. And I should say, of course, that this remains the subject of active research. Hence we can sometimes find them and under certain conditions, but it's no way as complete as the understanding we have for equilibrium statistical mechanics. And as I said, so the most important thing to note is that on average the particles are going to be moving, unlike equilibrium. Okay, so I should say that computer simulations will also help us provide insight into how one develops this framework. And I'm just going to show you here some simulations from my former postdoc, Majid, of a numerical model and these experiments by Paddy, Jerome, and Abraham. And this numerical model and these simulations, of course, capture the behavior seen in the experiments for various ranges of parameters. And so we can get, so there we saw the amoeba phase. Here we can see the sort of the flocking gas phase, and then here we can see that one of these flocks can then coalesce into huge moving objects which span the system. So now using our two control parameters, which was this activity or the driving or the crowdedness density, we can obtain a phase diagram. And I should say the white objects are experiments and the dark ones are the numerical simulations. So we can see that the simulations are able to identify the boundaries between the different phases. And again, one can go into detail of phase diagram, but the main thing you could say is that at low driving, at high driving, which is up here, and low densities, we have this flocking gas phase. And at low driving and high density, we have this new amoeba phase, which you could not see, which, as I said, is basically not possible for a normal material. And in fact, at very, very low driving, it looks just like a passive material. You get the crystal at high densities and low driving. Okay, so let's just try to summarize what we found about how to do statistical mechanics of active matter. So we have, in this case, microscopic dynamics with large numbers of degrees of freedom. For matter equilibrium, we have conservation laws. These conservation laws tell us how to calculate probabilities, and then and also tell us that that the system is stationary on average. For the active matter, we have microscopic dynamics without conservation laws. We can identify some functions which are somewhat analogous to energy, but what in general, the average particle is going to be moving. So these systems do not stay put, they move. So in some sense, the space of possibility is larger. So equilibrium systems only basically stationary, everything depends on the probability. Here, things will depend both on the probability and what the particles are doing. And studying that is essentially a lot of what we're doing these days. So so maybe I want to close by giving you some perspectives on these sort of active materials. So basically, first thing that I want to say, so I think the way in which we're going to describe them is going to be using some form of statistical mechanics, which requires that we're going to describe a typical particle rather than all the particles. And I should say statistical mechanics has had 100 years of success describing properties of matter, and it's the basis of basically all of our modern technology. And I would say that we are currently, with fits and starts, extending this framework to describe these new active systems. And in the case of myself, my collaborators, we've studied successfully a simplified, controllable experimental system where where our framework seems to work. And I guess we will see how useful this is for application to the real world in the future.